Very good. So what do we start with? We start with dynamic memory allocation. For many of you, this might look like a stupid topic, but for those of you that come from Fortran, this is a real big thing, because now you're allowed to allocate memory, a matrix or a vector as you need. If you need space, you just allocate it. The language, the operating system gives it to you, you work with it, and then you free it. In Fortran 77, you cannot do that. Even though we are in 2012, you will be shocked to see how much of the scientific code is still written in Fortran 77, which means there is no dynamic memory allocation. Fortran 95 allows that, finally, and so now this is becoming more and more common. So how do we allocate memory in C? With malloc. Malloc is a nice function that works in terms of bytes. Basically, it's a request to the operating system to return a portion of memory. As I said, it works in terms of bytes. So if you want however room you need, you have always to count in bytes. How to determine how much memory you need for a specific data structure? Well, malloc comes together with this function called size of. Size of takes a type, for instance double, for instance int or char whatever, and returns the size of one such data type. So one element of that data type. And then you know how many such elements you want, and you pass the request to malloc. Size of also works in bytes, so everything is coherent. You don't have to do any translation. In most implementations, I would say a double is 8 bytes. So if you want to allocate a vector of n entries of n doubles, you just say size of doubles, that will be 8. And then malloc will return an array, a piece of memory that is 8 times n bytes. The piece of memory, the memory that is returned by malloc, is just literally a piece of memory. It's just a space in the memory. It doesn't have anything to do with how you will use it. So the fact that you have used the size of double here doesn't mean that this memory is formatted, is seen as if it will contain doubles. So together with malloc, always there comes a cast operator. So maybe I should look into casting before doing that. Yeah, why don't we do that? So let's look at test 11, where I explain casting, and then we go back to test 10. So now I know that I should rename test 11 and 10. So keep the allocation, dynamic allocation on the back of your head for a little bit, and let's do a little bit of casting first, and then we go back to memory allocation. Casting. Casting in C means taking a variable, a quantity that is of a certain data type, and casting it, transforming it into another data type. Sometimes, for some particular quantities, casting is done through function calls. We have seen this already in part 1, when I was reading the input arguments, which, as you see, are defined as char, so as characters, but I was using them as integers. So I was using a to I to transform the argument into an integer. That was not casting. Casting is done with this funky notation, the parentheses. Okay, well, let me not run ahead too much. So let's start defining some variables, and then I show you what casting is. A is 5, B is 2 integers. C is also 2, but it's a double, so over here I used 2 dots to indicate that it's a double. Now I compute K as the division of A and B over B. And the question is for you guys, since you're an expert in C already, what am I printing down here? What will be the result? I'm just printing K, okay? Over here I say parenthesis D to show that I am formatting as if it were an integer. So and K is defined as an integer. So what will be the result? And while you think about it, I compile this thing. Test 11. Okay, what do I print? Come on, it's not even, it's a 5 divided by 2. It's stored into an integer, so what is it gonna be?
2.
Thank you. It's gonna be 2. So print K as an integer, it's 2. Okay. And now I have a set. Let's go step by step. Next, what I do is, now I compute Z as double, A over B, and I print Z. So what is that going to be?
It's 2 again.
It's 2 again. Why?
Because A divided by B is int, and this resides in an unknown, and this is then casted to double to assign to the variable.
So he's absolutely right. The result is 2 because the division is still an integer division. It's assigned to a double, that's fine, but the division is between 2 integers, so the result is still an integer. So the slash, when the arguments are integers, is the integer division. Okay. But I have more for you. Oh, yeah. Now, number 3. I hate this. How can I do it? Okay. Number 3. Now I take Z, which is 2, and divide it by 3. Remember, Z is defined as a double. So what will be the result of that? We know that Z is 2, okay? So now I divide it by 3. What do I print?
0.666.
Okay. Other takes? Other suggestions? Why is that now not an integer division?
Because Z is double.
Yes, precisely, because now Z is a double, so we will get 0.66. Next. What if I do that? Now I print Z. I know that Z is 2, okay? So I use D to print Z. What do I get? Garbage. Why garbage?
Because when it puts the argument Z on a stack, there will be 8 bytes on the stack, and when it passes the format string for %d, it looks for 4 bytes of int, and takes these, and the remaining 4 bytes are discarded, and it tries to figure out what to do with these half double as integer.
So is His answer is we're not going to get anything meaningful because over here I expect something that is 4 bytes long and I pass something which is 8 bytes long. Any other take? Could C be actually smart and figure out that, you know, I'm asking integer from a double, why don't I just convert it? Well, the answer is actually correct. First of all, the compiler warns me. No, it doesn't warn me. Why not? No, because I didn't save, that's why. So, first of all, the compiler warns me and says, hey, look at that. I expect an int, but you are passing a double. And even though it's just a warning, it's one of the, I'm not so sure whether to say nasty warnings or useful warnings. This should almost be an error. C lets you do these kind of things, and then when you run, you get exactly what he predicted, garbage, because I'm looking at 4 bytes of a number that is composed by 8 bytes. Okay, and next, finally, this is what a cast is. Now I transform Z into an integer. And it's not a function call, it's exactly like a function call, but the notation is completely different. It's a type to which I want to transform, and between parentheses. And then the expression that is being transformed. At this point, the result of this is an integer, so it's fine to print with D. And since Z is 2 to begin with, the output is 2. Okay, so these are 8 bytes compressed down to 4. So far we have not been able, yes?
What would happen if you print Z over 3 instead of Z? Would it be converted?
Say it again,
to 0?
if I print what?
Instead of Z over 3. Would it be converted into 0?
Yeah, sure, why not? Oh, you mean if it rounds up or down? Is that the question?
Okay.
Now let's move on. Other questions? Let's see if we finally get 2.5. After all, we're dividing 5 over 2. It would be nice to get 2.5. So, now I don't assign anything. I simply print the expression A divided by B. Remember, A and B are integers, and what I want is a double, so I use G. What do you think I get? What? I hear 2. Why is it 2? Absolutely, it is an integer division. So this thing over here will be 2. But the thing is that it's an integer, and then I am trying to print a double out of an integer. So the question is whether I will get garbage or not. So the compiler already warns me. It's the inverse scenario as before. Before I was looking at 4 bytes of an 8-byte number. Now I'm doing the opposite. It's just that we're lucky, or at least it looks like we're lucky. Can anyone predict what happens here? I am printing this thing twice. Can anyone see what I'm doing here? It's nothing special. I print this and I print that. So can anyone predict?
I have an idea.
Uh-huh.
Maybe the print takes the spaces after the string. So since A over B was transformed into a double and consists out of 8-bit, the first 4 bits. No?
A over B is 4 bytes.
Byte, it's a long byte. Okay.
Why would it be any different to the previous?
Oh, finally. I like this question. Why would it be any different? So let's see what I'm doing here. I'm asking for 8 bytes and I'm passing only 4 of them. Over here I'm asking for 8 bytes and I'm passing 4 of them. Then I'm asking for 8 more bytes and I'm passing 4 of them. It might be that these bytes, that this guy here doesn't get anything or gets something, gets at the, might be that this guy gets part of that. Let's see what happens. First of all, more complaints, more warnings. Look how beautiful this is. Be super careful, okay? It looked like everything was working, but it was almost a coincidence. Do you see the problem, right? Okay. So these warnings can actually save your life. Don't take them too lightly. Let's proceed. Let's do some more casting. So cast 1 and cast 2. Over here I transform, I cast what used to be integer 2 into a double and then I print it. And over here I transform 2 into a double and then I print it. So what will I get?
First is 2.
Mm-hmm. Yes, the second is not an integer division anymore. A stays integer, double B is now is a double. The division operator now recognizes that, so it turns into a double division, so this is a 2.5. Two and 2.5.
Why not the other way around? Why wouldn't it think it's an integer divided by a double, so convert both to integers?
It's just that I like.
Is that just how it is?
No.
Actually, it is because when it encounters a double and an int, it converts the smaller type to the bigger type, so to say.
But I think he means just that.
No, I mean,
Are you asking why I'm converting B and not A?
no, I mean,
Oh, okay.
what he's
Yeah, it's expanding the int to a double because double has more precision. It does the same to class, shorts, and ints.
You mean the division? What was the question? I'm sorry, I misunderstood.
So it's dividing A by B. A is an integer and B is a double.
Mm-hmm.
And so it converts A to a double.
Oh yeah, because of course there is an ordering, and double is more accurate, is broader, larger. So it always converts to the larger of the two sets. And I thought you were asking if casting A would cause the same, and yes, it does. Okay. Now something else. Now I assign Z to A divided by C. What is a C? C, if you go back, it's a double and it's 2.0. So now I am performing a double division. real division. Here I take Z and I print it with G. And over here I'm using these three functions for which I believe I need math. Yeah, I need to include the math library to use floor, ceiling, and such. So, this is an easy one. What do we expect from these print statements? Mm-hmm. So the round function, you can set it. I'm not sure by default what it does, but it's settable, let's say. So you can decide if it's round up, round down, round to 0, closer to 0, and stuff like that. I didn't save. So in this case is round up. And yes, we have 2, 5, 2, 3, 3. Okay, so far so good. That was easy. This is not going to be as easy. Let's look at this first. So we know that Z is 2.5. Now I take floor of Z and I divide it by ceiling of Z. By the way, everybody knows floor, I hope. Floor and ceiling, okay? So, now I divide the floor by the ceiling, and floor and ceilings, of course, will be integers. So in one case, I print the result with a double, and the other case, I print the result with an integer. What will I get?
Zero and zero. Since it's an integer division, it turns out 0, since it's 2 over 3.
Mm-hmm.
And it's the same case as we had before.
So now we have one more warning, warning 77. I am line on 74, so 77 is down here. I'm trying to print a double with an integer, so something is not going to be nice. Good catch. It's also interesting how these things are integers.
They're doubles.
What?
They are floor and steel return doubles.
Exactly, I cheated. I said that they are integers, that's true. The numbers are integers, but the type is doubles. So the ratio is still going to be a double. That's why we have 0.667. And that's also why we get garbage over there. So be careful. Yes, floor and the seal return integers, but they're not integers. Okay, and finally, let's do a little bit more casting. So, one case is I want to work with integers, so I cast the C to an integer. And the other case is I cast each of them. Do you see the difference?
C is double.
Yeah?
And you cannot cast from more big to smaller.
Oh yes, you sure can. Yeah. Casting is great. For sure you can do that. Unless it gives you overflow, you can certainly do that. What I'm trying to show here is that even though the result is the same, these two zeros come for completely different reasons. Over here, I take C, which is a 0.667, and it just happens that if you cast it into an integer, it's 0 point something, it goes into 0. Over here, I'm now really working with the two integer numbers. This is the integer division, and okay, it just happens that these numbers are such that the ratio is a 0. But these two zeros are completely different. So I put this example to show that don't think that this is the way to perform the integer divisions. Here I am converting the result, which is already a double. Here I am performing the integer divisions. Why? Because I make sure that both of the arguments are integers. Okay. Enough for casting, so now we can go back to test 10, because now you know what this line is doing.
Is the cast actually necessary then?
Here, is it necessary? So if I don't cast, I think I get void. I don't know.
In C++ it is, but in C you can cast void star to anything and anything to void star.
Yeah. So
At least one of those is possible. So in C, malloc usually is not casted
because it's a void star.
and you want to avoid cast because if you cast something wrongly, you don't get an error message.
So the answer is that probably you don't need to do it, but you have to be very careful. So if you work with the doubles, probably you don't have to do it. If you work with the integers, yes, you would. But I'm not positive about this, okay? And notice that I didn't say anything about void because, yeah, in C it's a way around. You can do pretty much anything if you get into voids, and I don't want to go there. Another thing also that I will not cover are structures, fields. They are super, and type definitions. They are super important, but I will not cover them. Okay, what does this program do? The program takes something from the argument, from the command line. It says if we pass nothing, so if there is only one argument, it says, okay, please give me something. If we have more than one argument, which means at least one, really, we will use that number as a size of a vector. Okay, we want to allocate a vector, we want to define a vector, and the only way to do it is by taking a pointer, so this will be the starting point for the starting location of our vector. It will be. Then I ask the operating system to give me enough memory, enough space. Here we go. And now m, not star m, but m, so the pointer, I move it exactly to where the operating system gave me memory, gave me space. So now my m points at this empty space, and we have seen already last time, at this point I can start accessing this array, this piece of memory, as if it were an array. So I can go in steps of the same size as whatever I casted the memory to. So in this particular case, m of 0 will be a double, m of 1 will be another double, and so on. And I will store some numbers inside this array, the square root of the index, okay? Then what do? Then I print the vector. Let's see what print vector is. The prototype is down up here. So there is a double star, so I'm passing a pointer, which is the address of the vector that I want to print. I pass something to print. I didn't say that in C, if you want a string, you just define it as a char star. So a character, char or char, it would be one character, and char star is any string. then you just have to pass this string in double quotes and it's automatically taken care of. Char star would be a pointer to a string, but if you pass the quotes, it's exactly as passing the starting point of the string. And then I print, and then I pass n, which is how long the vector is. In C, there is no way from simply this guy here, there is no way to know how long the vector is. I always have to pass this piece of information. Okay, so then I print the vector. Then what do I do? I run over the vector again, and now I square all the entries of this vector, and I print the vector. Okay, and then since I don't need this piece of memory anymore, I free it. And you guys were right, I checked, the memory leak is when you don't free memory, so memory later on in the program is not accessible or it's not usable because it has not been freed. That's why it's called the memory leak or leakage. Okay, let's compile this. So what do I expect to see? I expect to see the square roots of 0, 1, 2, 3 up to the argument, and then I expect to see the integers. Maybe not. First of all, I need to pass an argument. Here we go. So first we have all the square roots, and then I square them, and so I get all the entries. Notice that always we start counting from 0, so we go up to 81. Okay. Questions about this? Otherwise, I go into some. Yep.
Well, if you would not set any values to the array m, then there would be inside the array what is put on the stack or on the or in the memory. So you could read out what's written in the system memory.
Sure, which is garbage.
If you really try to get a real large portion of data, you can just scan it and check what the user doing with RAM or.
If I need a large piece of data.
If you want to get a large portion of memory, you can just make the for loop and look at what's written in the memory and can scan what maybe you can get some sensible data doing this.
No, you cannot. Oh, well, you, you really want to push me. No, so you cannot access, you cannot go beyond the stack. So when you execute a program, you have some limits. You cannot just go anywhere in the memory. There is a precise area.
Malloc does not initialize it with 0 or something.
No, if you want to initialize with 0, you can use, I think, cmalloc, or yeah, cmalloc. There are calloc, yeah, or there are other mallocs to directly initialize. What I'm saying is that even if you ask for a very large piece of memory, you will not get a piece of memory that is used by other programs. This is guaranteed. Other questions? Otherwise, I get into something more hardcore. Pointers to functions. How many of you have ever used pointers to functions? You're a computer scientist. You're not, right? So you are a computer scientist. Yes. Okay, that's why. Okay, let's do this. I have 4 functions. 3 of them take a pointer to an integer, so just an address. And the 4th one takes an address and an integer. Let's go and see what these functions do. The first one takes an integer and returns the negative of such an integer, so minus n. The second one doubles the integer. The third one adds 1. And the 4th one raises n to the power of k. Notice that there are all of these stars n's because I do not pass an integer, I pass a pointer to an integer. So if I want to access the actual number, I always have to dereference it. All right, let's see what the program does. Did I comment anything out? No. So let's comment. First, go. I print I, well, I initialize I to 3 and I print I. Then I invoke function 1. I pass the address of I. Okay. Then I pass the address of I again to function 2. So what is the first print? It's going to be 3. What is going to be here and what is going to be there? Function 0 is the negation, function 1, 2, double, function 2 is +1, and function 3 is raising to the power of.
So it's -3 and -6.
So -3 and then -6. Other?
-6 and then 7, I believe.
-3, -6,
Was called function 0.
-7. I love it. Keep it coming. More takes.
6 and 7.
Yes, +6, +7.
Ah, you changed your mind. Okay. Other takes. Okay. Yes, the result, the actual answer is a 6 and 7. This is true because function 0, f0, is the negation, but here is f1. f1 is 2, and f3 is +1. The point here is that I is modified. If I only passed an integer, the function would operate, but it would not modify the variable. So since I want to change the value of I have to pass the address. And let me do this. So 3, 6, and 7. Second run. Yeah.
Can you go to the function 1, please?
Function 1.
So, is it necessary to put this bracket after 2 star?
After 2 star, you mean here? Does anybody know? I don't know if stars.
This is important notation. Yeah, so it will be
I don't know if what this is. So
Tyler might be smart enough to know that this is not a double dereference. But maybe it's stupid enough.
no, I don't think it.
The
Oh.
syntax would still be unvs, wouldn't it?
Okay, no complaints. So I guess you're right. Apparently, I am not sure what the precedence is in this case. Okay, I also will not talk about double dereferencing or double pointers, but something like this actually can appear. I just don't want to talk about it. Let's just leave it.
When you put the space there, wouldn't it still mean the same thing as without the space?
Yeah, sure. Yeah. No, I'm saying that objects like this, a star, star, and can mean something. In C, it's possible to double the dereference. You can have a pointer to a pointer. That's what I'm trying to say, but I really don't want to go into that one. So, part 2. Now I am defining this thing over here, and that is indeed a pointer to a function. This is just notation. I don't think we can understand why this is a pointer to a function. This is what it is. So fpt will be the address of a function that takes an integer star. When you define the pointer to a function, you have to specify the prototype of the function. So you have to specify exactly what kind of arguments the function will get. That's why here I put integer star. And these parentheses are necessary. So now I know that fpt will be the address of a function. And how to use it? This is how to use it. I can simply take the name of a function and assign it to fpt. Now the fpt from now on will be the function fun1. So I can use it as a function. I know that fun1 takes a pointer to an integer, and so I can simply invoke fpt with a pointer to an integer. Or I can use the more verbose syntax, and these two things are exactly the same, okay? What is the result here? Fun1, and I do that. What do I expect? Fun1. I hear a 20. Anybody sees a 20? Yeah? You see the 20? Okay. At least two people see the 20. So I created a pointer to a function. I assigned the pointer to the function, well, I assigned function1 to the pointer, which means fpt now in memory points to where whatever fun1 is. Fun1 we know that is 2x, it's the double. Over here I call fpt, which is fun1, so I double I, and here I said these are equivalent ways. The syntax is equivalent, so I double 5 2 times, so hopefully I get 220. 520, very nice. And keep in mind, I have overwritten I, okay? This is not just a computation, I has been modified. Next. Over here I defined another pointer, but now it's a pointer to a different prototype. And clearly I'm going for a pointer for function 4. Function 4 takes an integer and a pointer to an integer and an integer, and now I'm defining a different pointer. And, well, function 4 meaning 3, because in C we count from 0. Then I assign it, and this is how I call it. So what do I expect now?
25 and 625.
Fast, yes. 25, it's computed here, and 625 is computed here. And again, I has been overwritten. So if here now I printed I would get 625 again. Okay? And now we move on to the last. Now we're going really all out. We're giving our best over here. Now we define an array of pointers to functions. And now we can do that, unless we play with voids, which I don't want to do. We can do this only with the functions that have the same prototype. So I am defining an array with 3 elements. What is in this array? It's 3 pointers to functions that take integer stuff. And now I can use the array like any other array, and I say the first entry is function 0, the second entry is function 1, third entry is function 2, and then I do this cute little thing here, and please predict the outcome.
-5.
That was fast. So we have a -5.
-8.
Keep it coming. I have to count myself. Let's see. Okay. So we have 2 votes for -5. We certainly have more than 4 people in class, so let's keep voting. Come on, guys.
Why do you start indexing this to?
Okay, my vote goes for -8. So maybe you should start putting some x's next to -8. I started from 2 and I'm going downwards, right? So this first one will be function 2, which was 2x. So from 3 we, no, function 2 was +1. So from 3 we go to 4. Then we invoke function 1, which is times 2. So we go to 8. And then we call function 0, which is negation. So I'm pretty sure it's going to be -8. Congrats to the brave -8. Okay, do you guys have questions?
What will happen if we don't match the arguments? Or if we subscribe a function with another signature? Or if we give arguments to the function without? Or something like that. What about errors?
Yeah, most likely the compiler will catch the problem when you, so for instance this,
Yes.
most likely the compiler will give just a warning. Yeah.
So can you give
That's just a warning. Oh. Okay. Yeah.
Can you give an example of why you would ever want to point it to a function?
Before the last example, I thought that too, but I mean, with only one variable, you invoke all the functions.
Yeah, exactly. If you only have a function, I don't really see the point. If you have many functions, you can use one address, and you can have a function that assumes different meanings at different points. And also, having worked in Mathematica, you should now think at a higher level. Now you can work with functions. Now you can operate with inputs and outputs with functions. That's why you take pointers to functions.
when you have a function that returns a pointer to a function?
When you have a function that returns a pointer to a function.
Just what you just said. At a higher level, can you declare what signature that function has?
I have no idea what you're asking, but that's okay. I don't know what you're asking.
Function returning a function.
Yeah, a function returning a function? Sure.
How do you know whether this function that is returned takes one integer or two doubles or something like that? Can you know?
Probably, wait.
The return type also has to have the proper signature. So, you have to
So look, it's here. This is, anyway, this is the output. This is the return value. If you're saying that you want a polymorphic function, sure, you can have that. That's what void is for.
For instance, if I want to assign df 0 equals and then a function call that returns me a function.
Mhm.
And the function I get returned is not a function that takes one integer.
Well, if you wanted to do that assignment, you could not use this one, because here you only take functions that return integers. So you would have a different prototype altogether. Okie dokie. Now let's go into something that is more performance related. Over here I wrote a program to add two matrices. So first of all I wrote something to create two matrices. Where is the chalk? Here. So what do I have here? Let's see. I ask for two arguments so that I have M and N, possibly in the other order. I never pay too much attention to this. And first of all, I initialize these objects with some data. And then, so I do that for two matrices, A and B. And then I build C equals A plus B and D equals A plus B. But I do this in two different ways. So first of all, how many of you can see, let me comment out everything after this. Memory leak, I wasn't freeing D. How many of you can see whether I am allocating the or initializing the matrix by columns or by rows?
It's by all.
Mm-hmm. So you say by row.
Yes.
We have one vote for row. How many of you vote for columns? I want at least 5 votes. Come on.
Row.
One more row. I heard the column. Row.
We had another row there.
Nobody for columns? Okay. So the way to show, to find out, is simply to print this I plus jm. And if that object there, if the numbers coming out of there are 0, 1, 2 incrementally, then it's by columns. If they jump, then it's by rows.
Imagine the plus sign is a comma, and you see that you're incrementing the.
Wait, 1 second. Say it again.
If you just imagine the plus sign as a comma, so you have I comma j. Okay.
Mm-hmm.
Then you're incrementing I, which is in the,
Mm-hmm.
row.
And what is that telling me?
That you're incrementing by rows first.
So you're saying, I like to hear this, I and then jm. You're saying,
I mean, the times m is just because you're storing it as a 1D array, so that's really not so important.
well, I have to store it as 1D array because there is no other option. I allocated a matrix as a really long array, so I only have a string. And now I have to figure out whether this is stored like this, so it's cut into pieces which are like that, or if it's stored like this. That's what I'm asking.
What I'm saying is because you're incrementing the I,
Mm-hmm.
which is the leftmost increment, I don't know what you call it. And
The innermost, you mean?
yeah,
Because it's inside? Then you're saying we are going by columns,
by rows.
by rows. I don't see that.
It
Do-
depends on what you use, how you define I and J. If I is a column or a row,
Exactly, it's so far we don't know what I is or J is. It's just a number.
If you swapped it so that the first for loop was for I, and then the second one was
Mhm.
for J. then
So
it's
if I
clear-
swap these two,
yeah, then it's clear that you're incrementing then by columns. But right now, if you're incrementing by rows, because the inner loop corresponds to the I.
yeah, but nobody says that I is rows or columns. Certainly C doesn't know if I.
But this is why I say if you imagine it as I comma J,
Mhm.
then I is the row position.
Ah, okay, so that's your assumption. Okay, now you're saying if I is the row and J is the column. Is that what you're saying?
Yeah.
If I, okay, then yes, sure. But the point is, you have to decide whether in memory, so let's put some numbers into the array. Alpha, beta, gamma. Gamma was awful. Gamma. Delta. No, delta. Thank you. Delta. Epsilon, and so on. Now we have to decide whether in the matrix these are actually like this or they are like this. The matrix will be seen by columns. Oh, well, actually, no, this is not even true. This also depends on how you traverse it. So, what I'm saying is, why don't we print out these guys? Mhm. And, okay, this is consecutive. So, if you imagine that your matrix will be seen by columns, okay, so this is stored by columns. If you imagine that your matrix is seen by rows, then, okay, this is stored by rows. You see that these elements are consecutive. So, if you envision your I and J in a way, then it's stored by columns. If you swap I and J mentally, then this is stored by rows. It's just a matter of notation. It's matter in your mind whether you put I and J in a way or the opposite way. What is really important is two things. One, to keep in mind what the libraries that you will use want. So if they want the matrix to be stored by columns. And two, if you store the matrix in a certain way, your algorithm should access the matrix in the same way. So right now we have used the JI ordering, and I want to show you the difference in performance in these two pieces of code. Over here I'm adding A and B following the same ordering, Ji. Over here I'm adding A and B with the inverse ordering. So I'm doing nothing different. I'm simply taking two matrices here. I'm taking two matrices, and in one case, so let's say that I have written into the matrices by columns. In one case, since I've written by columns, I am also adding the entries like this. So I access the first, the second, the third, and I'm computing C just by following the same ordering. This is case 1. Case 2, I have stored the matrix by columns, but I compute it by rows. I have swapped now the indices. Okay? And so I'm computing this by rows. In one case I follow the grain, and in the other case I go against the grain. Performance will be completely different, and I will explain why. Nope. We have to remove this. So I have at least a factor of 2 of difference. And we can do it with matrices a little bit larger. Still, this is almost a factor of 3. Here it's almost 4. We can a factor of 3, sorry. Do you guys see what's happening? I want to try something. Now I'm curious. Yeah, okay. So in all cases, there is at least a factor of 2 of difference. So how many of you know what a cache line is? Except for those, wow, except for those that have taken my class already. Everybody knows what a cache line is. So who doesn't know? Oh, no, okay. Then I will explain what a cache line is. When we ask for a malloc, we get a piece of memory, which is unidimensional. And this will be stored, this will contain, let's say that this is a double, another double, another double. So this is already multiple bytes. But let's just say this is a number, another number, another number, and so on. Okay. So when I want to access part of this memory, maybe here there is my number x, which sits right here. And I want to do something like x equals x times divided by 3. For instance. Well, I can only perform this operation if x is moved from memory into a register. So I need to go into the memory, fetch this piece of data, bring it to the register. At that point, the register will do the math and will store it back. As I do this, maybe I don't have to go to main memory. Maybe x is in the cache. That doesn't matter. What it matters is that into the registers, I will not get, well, okay, into the cache, I will not get only X, I will not get only this piece of data, but I will get more. This is called cache line. It's the minimum amount of data that is transferable. Even if I only need X, the processor cannot access only X, but it accesses an area around it, which is called cache line. Different processors have different cache lines. Sometimes it's 4 doubles, sometimes it's 2 8 doubles. It depends on the processor. So, what does it mean? It means that even if you have never asked for this location, for this piece of data there, that piece of data is available to the processor. So, since the processor has made the effort of bringing it into memory, why don't we use it? You might say, oh, well, who cares? I only need X, and in the next iteration I need my Y, which is here. So, I don't need whatever is around X, just give me my Y. Well, moving the data from memory to the processor is hundreds of times more expensive, between dozens and hundreds or even thousands, depending on how far the, the data is. It's dozens, hundreds of times more expensive than doing computation. When you work in high-performance computing, you will realize that it's not about how fast the computation is, but how efficient the data movement is. So it's all about amortizing the cost of moving data. Since I have spent cycles, time to move these pieces of data here into the processor, I should do my best to actually use this data. Now, if I store the matrix by columns, and then I access this object here, I pay the price not only to retrieve this piece of data, but also to retrieve these guys. So if my algorithm traverses the matrix in the same fashion as the data has been stored, I pay the price for this initial guy, and then I don't have to pay anything for the next 3. Instead, if I pay the price to fetch this piece of data, and then I move on to the next entry, which is over here, I have to pay the price again to fetch this piece of data. And then I ignore these guys, and then I go here and I have to pay the price again. All of these are called cache misses. It means that the processor looks hopeful to find the data that you're using into cache, and instead it doesn't find it. Why? Because it brought all of this portion in cache, but you're accessing something that has nothing to do, and so it's a cache miss, and this means that the processor has to go into main memory or at lower level of cache to fetch the data. So this is much more expensive. Things are even worse if you use prefetching. How many of you know prefetching? Not very many. So the processors nowadays are even more aggressive than just using cache line mechanism. They use prefetching. The moment you access a piece of data in this cache line, so this is a cache line, just because you have touched something in this cache line, this ignites, it triggers a mechanism so that the processor goes in memory and fetches the next cache line. Okay? So not only will this piece of data be available, but also the next cache line will be available. In fact, different processors have different cache line mechanisms. Some of them fetch even the two next cache lines. And you can set these yourself in some processors. Okay, this thing can get much more complicated because you can set different policies for different levels of cache. I don't want to get there. This only means that if you store the matrix in a fashion, you want to access the matrix in the same fashion. And you see a factor of 2 of difference just adding a matrix going by columns or going by rows. Okay? Now, in the latest processors, in the newest processors, this difference is only a factor of 2. Back in the days, it used to be an order of magnitude. Nowadays, these guys are so freaking smart. They decided to put in the processor not only a module for prefetching, but also a module for not branch prediction, but access prediction. So this module looks at where you're accessing the matrix and tries to identify a pattern. If it turns out that you're accessing the matrix by rows, the prefetching will be switched, and so the prefetching will not happen along the memory grain, but it will happen according to the pattern that has been identified. This is a super advanced stuff, and that's what the newest processors have incorporated. So back in the days, the difference was even more substantial. Questions about this? The next example, I think I will postpone to another time. I prepared a piece of code to, which is not this, it's this. I prepared a piece of code to call BLAS, so to do a triangular solve. Let's say I only want to say a few things, and then we look at the code the next time. But a few things to interface C with BLAS. So BLAS, by now everybody knows what it is. LAPACK is the same story. Both libraries were invented, were written in Fortran. Nowadays it's not necessarily true anymore, but still both libraries assume that the matrices are stored by columns. So when you do all of your reasoning, just keep in mind that everything needs to be stored by columns. This is especially true. No, okay. Just keep that in mind. And now the problem is these libraries are Fortran libraries, and we are using C, so we need to interface two languages. How to do that? Well, here is the first artifact. We will call a TRSM, so a triangular solve. The function in Fortran, the routine, is called TRSM. Yet, we have to add an underscore. This is due to interfacing reasons. There are ways to have the compiler add this underscore for you, but it's much better if you just do it yourself anyway. Since we will, as part of this program, we will call the TRSM, we need a prototype so that the compilation goes through. So we have to go into BLAS or LAPACK, open the Fortran code, and I guess we can do it the next time. Look at the prototype and write it here for us, put it here for the C compiler. The one thing to keep in mind is that Fortran wants all the arguments to be passed by reference. Reference means by address, so that's why we have stars on every single argument. Even though these are constants, even though these are integers, it doesn't matter, we have to pass the pointer to these objects. And then we will have to link against the BLAS, so we need to have BLAS installed somewhere. Let's just say that we look into this next time. So I will, maybe not Tuesday, because Tuesday we will solve the assignment. I don't know how long it will take. If there is time, we will continue with this. Otherwise, we do it next Thursday. Questions? No questions. Bye-bye.